Hello everyone, thank you for joining us for today's webinar, NPVS Open Pit Optimization featuring Stockpile Management. To introduce our presenter today, welcome Lee Poulin. Lee has been a mining consultant with CAE Mining for almost 3 years now. He is a graduate of the University of Alberta and first worked for Teck Coal as a drill and blast engineer and then made his way into mine planning. After a few years of freezing winters in the Rocky Mountains, Lee relocated to New Zealand. Whilst there, he spent the bulk of his time scheduling and optimizing open pit coal for solid energy. In 2011, Lee joined CAE Mining and made the move to Brisbane. Thank you, Lee.
Thank you, Eloise. So welcome to the webinar today. Yes, we'll be looking at NPVS, focusing mainly on what it can do as far as stockpile management. So NPVS, for those who don't know, is our open pit scheduling solution or optimization solution. It does do Lurch-Grossman optimization. So you start off with your geological model, your economics, and your engineering constraints. And once we have those, we're able to bring it to an ultimate pit. And we believe that with this software, that your ultimate pit that you can generate can be very close to what would be real, or close enough that you can make good decisions for the future. So the MAO and the MFO models are modules for the software are what allow you to see the effects of stockpile management. So MAO is the material allocation optimization. What it does is the mining schedule in the pit stays the same, but the destinations are changed. So material can be stockpiled and blended to reach the targets. And what material flow optimization, or MFO, does, it has all the features of MAO. And the mining sequence will stay the same in the order in which the blocks are extracted, but the extraction rates can be allowed to increase the net present value. So this is a brief overview of what NPVS does. So the first step in NPVS is that we import our data. All that needs to be is a block model. We can also import other things such as strings and wireframes. Once that material is in, we do up the economic model, which applies a value to each block. The next stage is the ultimate pit optimization, which uses the Lurch-Grossman algorithm and the values from the economic model to give you a final pit. Once you're happy with your final pit, we're able to generate the pushbacks. And with pushbacks, we're able to get our schedule. Once that schedule has been prepared, at that point we can bring it into the MAO and MFO. Alright, this is some data that you might want to prepare as well as when you're preparing your block model. I list that you can have boundaries such as lease limits, property limit costs, and obstacles. We can have capital costs associated with these and use those in the optimization. So here's an image of importing a block model. We are able to take regular or sub-block models from both Datamines or Studio 3, but also Surpack, Micromine. These block models, when they come in, the system can reblock them as it needs to. And all the user has to do is map the rock types, density, products, and attributes. And at this stage and at any stage in this process, there are reports, so you can check and see the result, see if your block model came in properly. So doing up the economic model, this is to determine the LG block value. I just have the notes here. I guess if you're just starting a project, first pass, we can do basic settings. What does happen with that, as long as they're proper in terms of scale and effect, that your mining sequence will probably be very similar to what happens when you put in more detailed costing. The costing, we build in mining costs, processing costs, reclamation costs, and also the pricing or value of the different products. There is different set ways in the system for it also to determine what blocks are ore and what blocks are waste. So for our ultimate pit, the inputs are, we set up our slope angles, which can be by area, by rock type, or general. We set up our production rate as in terms of ore input, or ore run of mine from the pit, and also year-by-year discounting. At that point, we're also able to set up what period our discounting is based on, normally a 365-day year. At that point, we are also able to set up our boundaries and control surfaces, such as those capital costs or obstacles. As a note, so we can run the Lurch-Grossman algorithm to get the final pit. If you already have a pit design, it will run the Lurch-Grossman optimization within that pit if you so choose. Or we also have a different search algorithm that, instead of trying to optimize NPV, will schedule blocks together to meet blending requirements. So once we've generated our LG phases, we're able to see them. The LG phases can be by price factor, profit factor, or cost factor. With the LG phases generated, we then get what is specific to NPV Scheduler, the optimal extraction sequence. And from the ultimate pit on, the OES is generated and feeds the next stage of the process. So this means that each block has been sequenced for maximum NPV. So this sequence would be the same whether your time periods were broken down by years or quarters or months. The sequence should remain the same. And that means that your NPV should be maximized always, no matter what time scale you look at. So with our pushbacks, they are using the OES from the Lurch-Grossman optimization. And we're able to specify a target size for the pushback, and the system will go through and create a pushback that has at least the amount of ore that you specified. Another thing that it forces is it will take blocks that are adjacent or touching. It will not break up the pushback into different areas, and it uses a minimum mining width. We also have the option to control either each pushback individually or only some of the pushbacks by string boundaries, and those can be done dynamically in the program. Once we have our pushbacks, we can feed it into the scheduler. Our scheduler is forward and backward looking. It maximizes NPV over time, not just finding the maximum for each period before going to the next period, but it builds up a decision tree, and we are able to optimize not just on NPV, but on multiple targets. We can give the system as many targets as we want, but we do specify what is the primary target. These targets are adjustable by period, and we can also assign capital costs by period that will affect the NPV. So by being able to adjust many of these things by period, targets by period, it means that we can have a schedule that gets us very close to what you would actually, close to what you would do in the pit. It would be realistic, achievable. Once these reports are generated, we can export the block model and to Studio 3 or other packages. The block model does have the information on the blocks about everything from the data that was imported as far as qualities, the economic model values, the ultimate pit Lurch-Grossman shell and the OES, pushback shell and OES, and the scheduler period and sequence, and also destinations. Up to this point, other things that we can export are shells, pit rim strings, and our reports. So once you've run the schedule, everything has assumed that the material is processed in the year that it is mined. With MAO, or the Material Allocation Optimizer, the pit will still be mined in the same sequence, but we are able to change destination for optimal blending. We're able to have multiple processes, plants, stockpiles, and targets. So I'll just quickly go through some of those settings, and then we'll go into the demo. So with MAO, you are first able to update your economic settings. In the demo that I have to show you, initially there was the assumption that there was only one plant with an average processing cost. But in the economic model, we were able to set up for the MAO run that there are actually multiple plants. They have different processing costs. So now the system will be able to choose between them. Another important feature of MAO is we're able to set up binning. So your ore blocks, as they used to be just in our schedule blocks, now they will be separated or classified based on some ore categories. We do have this we can have it very simple, based on a single quality, specify 10 bins, or we can have multiple qualities, and the system will generate bins from those. Or if we have very specific needs, we can define the bins ourselves. We are able to set up two different kinds of stockpiles. So the first type of stockpile is a single ore type. It only takes one rock type from the pit. And that rock type, once it goes into the stockpile, will then have the option of using the processes as defined in the economic settings. Type 2 is a complex stockpile. It can have multiple inputs, both from in-pit or from external sources. It can also have a processing component to it, so something like upgrading ore qualities. And because it can have that processing requirement or external inputs, then it has the ability to redefine what destinations that ore can go to. In each of these cases, we have size, feed rate, and reclamation controls, and these can be either global for every time period or adjustable by time period. We also have, for our destinations, we can set up our quality controls, which are both constraints and targets. Constraints are applied to material coming into the destination, and the targets are for material leaving the destination. So post-blending. And we've already... All right. So that's our basic overview of our settings. With Material Flow Optimizer, it has all the features of MAO, but it also adds the ability to change the open pit mining rate. Your schedule sequence from your schedule will remain the same, but you are able to mine faster to get more material in. What it's doing is it's trying to increase the value of the mine by bringing higher grade ore forward and stockpiling low grade ore or stockpiling or dumping low grade ore for processing later. So I have here a MAO project. So the original schedule ran for 24 years and had an NPV of 22.6 million. This is the case where there is a single plant, processing plant, and its costs are fixed. But to set up my MAO processes, I can look at my economics, where previously there was, yes, a single plant. Now I have two plants, and they have similar unit costs, but additional processing costs applied to the refined ore. So, yes, the original plant had an additional processing cost of $150 per ton of product ore. Our new processes are either $140 or $170 per ton. And we'll see further on that the differences between the plants is that they can also have different feed grades. So here's my MAO settings. I only have one rock type, and the aluminum in it is a waste product. So we want to control the aluminum grades that are going into the plant. So we've got a simple one grade, we've got 11 bins. We have created one simple stockpile for that ore. The stockpile has a maximum size of 10 million and can feed the plant at a rate of 1 million tons per year. Because this is a mine that we're starting from the beginning, there is no material to start off in the stockpile, and with no material we have no grade, initial grade in the stockpile. We have no complex stockpiles, so if we did, then we could set up where they would go. Alright, so the destinations for anything that comes out of the pit are either Plant A, Plant B, or the sulfide stockpile. So Plant A, which is our lower cost plant, can process a limit of 2 million tons of ore per year. Plant B can process a limit of 1 million tons per year. The original case had one plant with 3 million tons per year. And here our stockpile can receive an unlimited capacity per year, or yes, this is a rate-based, because we've got a storage capacity of 10 million, so the maximum that it can receive at any point in time is 10 million. With the plant, we have limitations for what we want to get out of the plant. So we want a maximum AL203 of 0.7, and our EAO, we want a maximum of 1.8. With the plant B, the higher cost plant, we have no limitation on the AL203, but we do have a higher maximum for the CAO. And we have no global settings. So yes, in this case we were running MFO. So looking at the initial schedule, we had an NPV of 22.6 million. Now that's based on having the one plant, but it quite often will be that we would have a situation where you have different processing methods. So my new NPV, once I've changed my processing sequence, is 18.5 million. It is lower than the previous one, but I'm okay with that because I know that my plants are different and that it needs to make some choices there so that it can reach the grades required for the lower cost plant. Another thing that I can show here is I've got my schedule. You can see that mining occurs in the schedule, mining occurred over 24 years. And with the MAO, the mining also occurred over a period of 24 years. But there are an additional 4 years where material is coming out of the stockpile. So, and here's the size of my stockpile over the years. How much is lists how much is coming in and coming out to be blended. I've got another case where I have set up the material flow optimization. So this is using the same settings as the MAO, but I have allowed my mining rates to change. So the initial schedule had lower rates, but I've set a maximum mining rate of 7 million tons per year for the first 2 years and 4 million tons for every year thereafter. And for this simple case, I will go to my summary. So the original case was 18.4 million, and by allowing the schedule or the mining rate to increase, we are able to increase the value from the 18.4 to 19 million and shorten the mine life. We do short the mine life as well. So that's, I think, gives you a fairly good overview of what MAO and MFO can do. So the blending that it does is on top of what the schedule can already do for reaching targets. Now I guess if there's any questions, Eloise?
Thank you very much for that, Lee. So we have one question here, which is MAO just bringing forward higher grade, or does it also include a blending component?
So, what MAO and MFO are doing in both cases, they are blending the material, but they are not changing the sequence of what's coming out from the pit. So as the schedule would have already determined which blocks are coming out from the pit in a certain order, but with the MAO and MFO, MAO will not increase the rate. It will just take the blocks as they come out of the pit and make the decisions based on target grades and what's allowable for each different plant. So it will stockpile, blend to try and reach those targets. With MFO, the blocks will still come out of the pit in the same sequence, but they might come out earlier so that by bringing them out earlier, you can maybe move the low-grade material out of the way, put it in the stockpile, bring up some high-grade material earlier, and blend that into the earlier years to increase your NPV.
Great, thanks for that, Lee.
All right. Good.
Okay, and then we've got another question here. By maximising NPV, do you take into account the capital cost? That is, can you put equipment requirements into this system?
All right. Yes, we can put. We can't put equipment costs into the system. If you're talking about shovels and trucks, then we don't put those capital costs into this. Well, actually, we can put capital costs into the system. See, I'll show you here. So when I'm setting up my when I'm setting up my scheduling settings, I am able to put in capital costs either by pushback or by time period. So if I know when I'm going to have different fleet requirements, or there's a requirement to bring different fleet in, I can then assign that to different years. I know from your comment that you're saying that there are years where your waste movement goes up and down. We are able to, in the scheduler, I guess, if we set the primary target as NPV, then the waste movement will vary as it needs to reach the maximum NPV. But we are able to put in constraints as far as rock movement. So I can come and set a target. Right now, I can add a target that has my rock. This can be my rock tons. We can say that in any given year, I can have a maximum of 7 million and a minimum of, we can allow the minimum to be 0, but our target should be something around 5 million. And so if I set this target rate and have the system not just report it but track it, then it can create a schedule where it will still try and maximize NPV, but above all else, it will make the rock tons. So by that, I'm able to control the rock tons per year. I'm able to get a schedule that is achievable. It doesn't require you to bring in extra equipment for 1 year, then send it back, bring it again 3 years later. But yes, we can apply the capital costs either by pushback or by year.
Thanks, Lee. The next question we have here, partial percentage in block model, how are they handled?
Okay. So a partial percentage in the block model. If I'm understanding this right, in the block model, because we allow sub-blocked models to be imported, what happens is we have our different rock types defined in the model. So any blocks that come in as a certain blocks will come into a parcel specific to that rock type. So if you have 3 rock types in a 20 by 20 by 10 block, that block in the economic model will retain those 3 rock types. The grades will be blended within those rock types, but the rock types stay separate within that parcel. And that means that in your scheduling it will still decide when it takes a certain block that ore type 1 will report to its processing plant, ore type 2 will report to a different processing plant. The waste will go to the waste stockpile. Hopefully that addresses it, but the material is kept separate in parcels in the parent cell size blocks.
Thank you, Lee. So we've got time for one more question, which is there any capability to perform cut-off grade optimization over all periods?
All right. I think this one might be something that I need to address later, because the questioner does specify a particular person. So I'll reply to this one in email. For those who are interested in the answer, we can send that out to you. So please request the information and we'll send it to you.
And if you would like to request that information in the feedback form that you'll be redirected to, you can add that in the other comments field at the end there. So thank you very much, everyone. This marks the end of the webinar. Thank you for attending. We hope you found the content presented valuable. If you did submit a question that we were unable to address, please rest assured these have been recorded, so we'll touch base with you afterwards to follow up. You will soon be redirected to an online feedback form. It will take no more than a few minutes to complete, so if you do have the chance, we'd really appreciate your feedback on how today's webinar went. We will also be sending out follow-up emails to all of our attendees, which will provide you with a recording of the webinar, as well as the necessary details to contact us should you have any additional queries. We look forward to hearing from you soon. Thank you all once again for attending, and thanks again, Lee.
Thank you.